Today, we're going to talk about something that sounds like it's straight out of science fiction. We're talking about designing materials literally atom by atom to solve some of the biggest problems we face. This is a story about a quiet revolution in how we create the very stuff that builds our world. I mean, just think about it for a second. What if you could build the absolute perfect material for any job? A material that's perfectly designed to snatch carbon dioxide right out of the atmosphere, or one that could safely and densely store hydrogen to power a clean energy economy. It really does sound like magic, but believe it or not, we're getting closer to that reality every single day. So what's the secret sauce here? Well, it's a special class of materials called metal organic frameworks, or MOFs for short. The absolute best way to picture them is like Legos, but on an atomic scale. You've got these metal clusters, those are your main connector blocks, and then you have organic molecules that act as the struts, linking everything together. And just like with Legos, by picking and choosing different building blocks, you can construct a practically infinite number of different structures. And this Lego-like design is exactly what makes MOFs so mind-blowingly special. First off, they have what's called immense porosity. They're basically all empty space on the inside. Get this, a single gram of a MOF, about the weight of a paperclip, can have an internal surface area the size of a football field. It's just insane. Secondly, their structures are completely tunable. You can swap out a metal piece here, change a linker molecule there, and you can totally change the material's properties, its pore size, how it interacts with light, everything. This basically turns them into a form of programmable matter, where we can design them from the ground up for one specific job. All right, so here's the plan for our journey today. We're going to start with just how massive this material revolution is and the crazy infinite haystack problem it creates. Then we'll see how machine learning is swooping in to save the day. We'll even pop the hood and look inside the ML toolbox. After that, we'll get to the really exciting part, the real-world breakthroughs that are happening right now, before we look ahead to the future of how we design, well, everything. So this all sounds amazing, right? We can build whatever we want, but there's a catch. A huge one, actually. The problem is choice. The number of possible MOFs you could create is so staggeringly huge, it's like trying to find one specific needle in a haystack that's the size of the universe. Just to give you a little perspective, right now, scientists have already made and cataloged over 100,000 unique MOF structures. These are real materials that exist in labs. Their structures recorded in things like the Cambridge Structural Database. That's a ton of materials. But hold on, because that's nothing. That's just the tip of the iceberg. Using powerful computer simulations, researchers have already mapped out over 1 million more hypothetical MOFs. These are structures that follow all the rules of chemistry. They should exist, but no one's made them yet. The chemical space of what's possible is just astronomical. And this is where we hit a wall, a massive wall. There is just no way we could ever manually create and test every single one of these possibilities. The old school way of doing science, make something, test it, see what happens, would take thousands of years and cost billions upon billions of dollars. Trial and error just doesn't work when you're dealing with a number this big. So how on earth do you search an infinite haystack? Well, you build a super smart magnet. And in the world of material science, that magnet is artificial intelligence, specifically machine learning. ML gives us the power to sift through, predict, and even design brand new MOFs at incredible speeds, all without having to mix a single chemical. So what are we asking the AI to do? Well, a few key things. The most common task is property prediction. You show the AI a MOF structure and you ask, hey, how good will this be at capturing carbon dioxide? Then there's high-throughput screening, which is basically speed dating for materials. The AI zips through millions of candidates to find the top performers. But the real magic, the real game changer, is something called inverse design. That's where you go to the AI and say, I need a material that does this. Go invent it for me. And it does. It designs a new structure from scratch. We're even starting to use AI to figure out the best recipes to actually make these new materials in the lab. Okay, so let's pop the hood for a minute. How does an AI actually learn about a material? It's not magic. It's a really clever process that's all about data, language, and some very powerful algorithms. You can break it down into 3 basic steps. First, you need what are called descriptors. This is how you describe them off in a language a computer can actually get its head around. Numbers representing things like pore size, surface area, the atoms involved. Second, you need datasets. Think of these as giant cookbooks filled with recipes and results for thousands of known MOFs. This is what the AI studies to find patterns. And finally, you choose your method, the specific AI algorithm that's right for the job you're trying to do. And that cookbook I mentioned, it's not just one book, it's a whole library. These huge public datasets are what fuel the entire field. You've got things like the core MOF database, which is packed with real experimentally verified structures. You've got the hMOF database with those millions of hypothetical ones. And then there are specialized collections like QMOF that focus on things like electronic properties, which is crucial if you want to design new types of sensors or computer chips. So when it comes to the methods, you can think about them in two main flavors. The first is property prediction. This is like playing detective. You give the AI a suspect, a known MOF structure, and you ask, what did this MOF do? How much gas will it absorb? But the second approach, inverse design, is so much more exciting. This is like being an inventor. You tell the AI, I need you to invent a brand new MOF that has these exact properties. This is where the really advanced stuff comes in, like generative models that can literally dream up atomic structures that have never existed before. Okay, enough with the theory. This all sounds great, but does any of it actually work in the real world? Is it making a difference? Oh yeah, big time. This partnership between MOFs and machine learning is already producing breakthroughs that could change everything. When you look at energy and the environment, the applications are huge. We're talking about using AI to pinpoint the perfect MOFs for direct air capture, literally sucking CO2 out of the sky to fight climate change, or finding new materials that can store hydrogen fuel safely and densely, or creating molecular sieves that can purify natural gas and make industrial chemistry way more efficient and less wasteful. And it doesn't stop there, not even close. Scientists are using these exact same tools to design materials for better fuel cells, for ultra-sensitive chemical sensors, but maybe the most amazing application is in medicine. Researchers are using AI to identify MOFs that can act like tiny programmable drones to deliver chemotherapy drugs directly to cancer cells, like in pancreatic cancer, while leaving healthy cells alone. This could totally revolutionize how we treat diseases. So, we've cracked the code, right? Problem solved? Well, not quite. The path to a future of fully automated material design is incredibly exciting, but there are still some major hurdles we need to clear and some amazing new frontiers to explore. Right now, there are kind of three big bottlenecks holding things back. First, even with all those databases, we're still short on high-quality experimental data. The AI needs more real-world examples to learn from. Second is what's called interpretability, the black box problem. The AI can give you an answer, but we need to get better at understanding why it thinks that's the right answer. And third, and this might be the biggest one of all, is synthesizability. It's cool that a computer can design a million perfect MOFs, but if you can't actually go into a lab and physically make it, then it's just a cool idea on a hard drive. But if you look ahead, you can see the next wave coming. Right now, we're seeing large language models, the same kind of tech behind ChatGPT, reading scientific papers to learn how to make MOFs. The next step is to bake deeper chemical intuition and rules directly into the AI, making it a true scientific partner. But the ultimate goal, the holy grail, is to connect these AI brains to robotic labs. To create a fully autonomous, closed loop where an AI designs a material, a robot makes it, tests it, the AI learns from the result, and then designs something even better, all on its own, 24/7. And this quote here really hits the nail on the head. The future isn't about AI replacing scientists. It's about integration. It's about building a dream team, where you combine the incredible speed and pattern-finding ability of AI with the pinpoint accuracy of traditional physics simulations. Together, they create something way more powerful than either one could be on its own. So that's where we are. We're at the beginning of an era where AI is no longer just a calculator, but a creative co-pilot for scientific discovery. We're handing it the map to this infinite chemical universe and asking it to show us the way. So the question is no longer if we can find the perfect material for the job, but which one of our impossible problems do we want to solve first?